Okay, thank you. Thank you for your kind introduction. And also thank you for the invitation to this EASF seminar. I'm really happy to share some of my stories about liquid crystal elastomers and also our micromechanics algorithms. So due to the time, let's start.
How do you mind change your view because with your backup slides?
Okay, so let me see. Let me stop share first. I do the, and then share with yeah, is it now working?
Yes, now it works. Thank you.
Okay, thank you for your remind. Yeah, so as many of you might not know liquid crystal elastomer, but it is a rising star material that has been attracting a lot of interest, and because such as it has been explored in many applications. In the first example, just like the viscoelasticity, previously Colette has just mentioned before, it has been used in the in the shock absorption materials, such as here it is used as a helmet, and also people have been exploring it to replace some of the human bodies. Here is an example where it is replacing the intervertebral disc implant, which is a part that is between the joints of our spines. And also because of its actuation behaviors, it can be used to do something like soft robotics. Here is an example that is showing a rolling machine that can be actuated by heat. So liquid crystal elastomer has a lot of fascinating properties. And our today's story will be started from an experiment that is done by our collaborators at Kyoto. So what they do is that they start with a liquid crystal elastomer sheet that is, they hold the y direction fixed, and then they gradually stretch in the x direction. So here are some snapshots of the elastomers during the stretching. And the left figure is showing you the stress strain curve, where the y-axis is the Cauchy stress in both directions. The dashed line is the stress in the x direction, and the solid is in the y direction. The x-axis is the stretch. As you would still notice that there is a certain region where the Cauchy stress in both directions are actually equal. So, but if we look back into the stretch, we could see that clearly the strain is not equal. So what it means is that the material is in a state where it has shear strain because of the unequal principal strain. But there's no shear stress because the principal stress is the same. So it reminds us of a property of the liquid where there is some shear strain, but there is no shear stress. So, but how do we understand this? That's the beginning of our today's story. To explain this, let's start with some of the microstructures of the material. So as its name suggests, it's a combination of liquid crystal and elastomer. So liquid crystal are a group of rod-like molecules. They are typically of two phases, where at high symmetry, molecules are randomly oriented, and at low symmetry, they are aligned in some direction. We also have elastomers, which is made by long-chain polymer. And then if we cross-link it, we would obtain the entropy-driven elasticity of the elastomer. But if we further embed the liquid crystal molecules into the long-chain polymer, we would get what we call the liquid crystal elastomer. So at high temperature, they will be oriented randomly, but if we cool it below the critical temperature, they will be aligned together. And because they are cross-linked with also the long chain polymer, so that this ordering effect would give rise to a microscopic extension along the aligned direction. If we further pattern which direction it aligns, it will give rise to a lot of complex behaviors. So this extension is not restricted. It could do any of these directions, like starting from the isotropic state, and even a combination of those. So there is a well-known experiment that is done by Finkelman. They start with a liquid crystal elastomer sheet, so where all the molecules are aligned in the same direction. And this sheet is actually transparent at the beginning. As we would know that if we stretch it, because they want to align or extend along the direction where the molecules are aligned, so that at the end, all the molecules will be in the y direction. But what is happening in between is that there were, to accommodate this strain that is applied to the sheet, it has this alternating direction pattern, so that in the neighboring stripes, the liquid crystal molecules are, or we call it mesogens, are actually orienting in the opposite direction. And if we average this extension out, you would get the microscopic strain as it is applied. This is confirmed by the experimental observation, where you could, if you have a zoom in picture, you will see these stripes. Because this reorientation of the mesogens are actually energetically much cheaper than the elongation of the polymer network. So if we stretch it, you would see that it is exerting much less force compared to a normal rubber. And this is what we know as a soft elasticity. But all of this is limited into a monodomain sample where all the molecules are aligned in the same direction, and also it is a 1D uniaxial stretch. So we further extend this into a more complex situation. So here are the systematic study that is from our collaborators, that they do a 2D stretch of the sheet. And so the first one is what I just mentioned before. And they also do some unequal baxial extension, where the ratio between the strain in X direction and the strain in Y direction, this ratio is fixed. So on the right-hand side, what I'm showing you is a sheet that is stretched with a ratio of 5:1. And at the end, we also have equibaxial extension, where the stretch on both directions is the same. So the right figure are the snapshots of the during the stretch. But as we soon will notice that while the sheet is all starting from opaque, the end point is clearly not the same. So that the first two are actually transparent, but the last one, while you are stretching it with an even larger area, but it's still opaque. So there are some interesting phenomena, but maybe just let's set that aside and take that into our next discussions. So here's a summary of the stress strain curve of all the protocols that we have just mentioned. So the figure is showing you that the x-axis is the thickness, where as you stretch, the thickness will steadily decreasing. It is from right to left. And the y-axis is the Cauchy stress in both directions, where the dashed line is the Cauchy stress in y direction, and the solid line is in x direction. And for different color, it stands for different protocols. We will soon notice that for each same color or the same protocol, you would have that a certain range that the Cauchy stress in two directions are the same. So basically there would be no shear stress. And what's more is that for all the colors, you would have a universal line so that it is independent of the protocols. It is just a function of the thickness. So that basically the stress in the extruded from our stretch is only a function of the area of the membrane. As a comparison, if we do the same test on the normal rubber, you will see a very different behavior. Then none of these phenomena would be observed. So this is actually confirmed that this is a unique behavior of the liquid crystal elastomer. But how do we understand this? Maybe let's start with some of the energy of the liquid crystal elastomer. So here is if energy where if we omit this L tensor, it will be a normal neo-Hookean material. And if we have the L tensor, then because of this, you will have some isotropy where it is when the energy is minimized, it would be elongate along the direction of n, which is indicating the orientation of the mesogens, and it will have a shrink in the other two directions that is perpendicular to the orientation of the mesogen or the liquid crystal molecules. And as n could be changing, because it is just a unit vector indicating the orientation, as it is changing, you would see the energy minimization set is also changing. So that's the basic elasticity of liquid crystal elastomer. And along with that, we also have some other energies, which such as the liquid crystal elastomer will have a memory of its initial orientation, and in reorientation, that is from its initial direction, would have some energy cost. We also penalize the spatial variation of the liquid crystal elastomers. And at last, we also have the viscosity, which is important for this soft material. That's all the energy of the liquid crystal elastomer. And we see that the energy is very complex and might be a heavy computational work. To deal with that, we're actually using the graphical processing unit. We know that as GPU. Why is that? Is because there is a recent trend in the high performance computing that these accelerators, GPUs, are actually accompanying CPUs and even replacing CPUs for some computationally heavy work. It has been used in many HPC platforms. And the reason is that it also has many successful applications. For example, such as in the reconstruction of MRI images, and also the data accessing in the seismic database. What is more close to our mechanical society is that the molecular dynamics. There are a lot of well-built softwares that is including the GPU accelerations. So today's work is to take advantage of the computational power of GPU and to further help us solve the micromechanical problems. So given the energy, let's come back to the set of equations we have. So here W is the energy of the material and F is the deformation gradient. So this would be essentially the stress that is a function of the gradient of U, which is the deformation gradient. And also the N is the internal variable. Here is the orientation of the liquid crystal molecules. And basically this is a stress, and it should be in equilibrium if we have no inertia And that's the first equation. And we also have the evolution equation, which is telling us how the internal variable, with basically the orientation of the liquid crystal molecules, would be evolved during our stretch. So that's the second equation. And we could also rewrite these equations into a variational formulation, where basically, instead of solving this partial differential equations, we're solving a minimization problem that is with respect to the deformation displacement and also the internal variable. We will soon notice that the energy, which I have just mentioned before, is of a very complex form, and it involves a nested nonlinearity, but it is more complex because we have included the displacement, the gradient of the displacement, instead of the displacement itself. So to resolve this, what we end up using is that we explicitly write this apart. So here we introduce another variable, which is a deformation gradient, into the energy, and explicitly enforcing it to be equal to some displacement fields gradient. So this constraint is informed by a Lagrange multiplier and plus a quadratic penalty term. What's the advantage of this? So because here we have a deformation gradient and the displacement field, there are two variables. We could actually do alternating direction method of multipliers. So where we first minimize with respect to the deformation gradient and the internal variable, we will soon notice that if we are just minimizing that, there's no dependency on its neighboring material points, so that it could be solved in massive parallelism, because there's no gradient term that is that is spatially. And then we will minimize with respect to the displacement. That leads to a Poisson equation, which we also have a lot of fast solvers. Here we are solving it using some fast Fourier transform based algorithm. And at the end, we update the Lagrange multiplier and check for the convergence. So the first step, because it is local, there is no communication, we can actually take advantage of the GPU structure, where GPU is basically favoring a large, massive parallelism, where it has like typically thousands of cores in each single GPU card. And second is a Poisson equation. We're solving it using FFT, which can also be significantly accelerated by the GPU. So these two main steps could take advantage of that, and this is the key part of our algorithm. Maybe after that, let's show some of the results. So here is a simulation of the first example we showed it at the beginning. So the left figure is a stress strain curve, where the big one is actually the Cauchy stress, and the smaller one is the nominal stress. As we would first notice is that the orange, which is the experiment, and the blue is our simulation, is in a good agreement. And another thing is what we just mentioned, there is a region that is the Cauchy stress is the same, so there's no shear stress. And what's more interesting is that because of this equality of the Cauchy stress, if we further look at the nominal stress, we will see that the nominal stress in the stretching direction is actually much less than the stress in the holding direction. So it might have some interesting applications with that, such as if we stretch with in one direction, it will exert much force in the other. And another thing on the right figure is showing you the evolution of the liquid crystal molecules. So the color is indicating, the color is indicating the orientation of each molecules with respect to the x-axis. We will see that as it is stretched, the color is gradually turning into a uniform blue or green. So, and this is accompanied by the divergence of the Cauchy stress. So this is giving us a hint that the liquid-like behavior of the liquid crystal elastomer is actually a result of the reorientation of the liquid crystal molecules. And what's more, we can answer the question. So as it is uniform in the end, if we link it with the pictures that we see before, we will see that because of the uniformity, that the light can actually pass through the sheet at the end, so that the sheet will be transparent at the end of the stretch. As a comparison, we can look at the equibaxial extension case. So here, if we look at the evolution of the microstructure, we could see that there is basically no change in the in-plane orientations of the liquid crystal molecules because the color is not changing. And if we further look back into the liquid crystal elastomer sheet, and there will be no transparency change. The sheet is always opaque. We could also do a summary of the experiments with the simulation. We see that there is a good agreement that the simulation is not only capturing the liquid crystal behavior of the liquid crystal elastomer, we're also capturing the stress strain curve quantitatively. This is remarkable because our simulation is only using 4 parameters to actually fit in all these 10 curves. Other than that, we could also see the in-plane reorientation of the liquid crystal elastomers, where the left figure is showing you the wide angle X-ray scattering of the in-plane orientation of the liquid crystal molecules. The intensity is showing you the population of the orientation in plane. And we could see on the right-hand side is our simulated scattering results. There is a very good one-to-one correspondence between these figures. And this is also confirming our results that as it is stretched, actually we have the reorientation of the liquid crystal molecules accompanied to give rise to this liquid-like behavior, such as here, you will see that in the planar case or in the UB unequal biaxial 5-to-1 case, there is a concentration in the intensity of the liquid crystal elastomer sheet. And this is accompanied by the liquid-like behavior. With that, I would like to draw a conclusion. So we found a new state of the liquid crystal elastomer where it has in plane, it is liquid-like. So basically, shear strain would introduce no shear stress. But out of plane, there's rubber-like, because as the thickness reduced, you would have elasticity that the stress is exerting. We also present a new computational method about on GPU. Actually, we have not limited to liquid crystal elastomer. We have studied a wide range of systems, such as the bifurcation in some finite elastic problem, where the instability occurs. We have also applied the same idea into some origami kinematics. Here is showing ongoing research of our work. With that, that's all my talk today. I would like to thank my advisor, Kaushik Bhattacharya, and also our collaborators at Kyoto. If you have any questions, I would be more than happy to answer.
Thank you very much. Excellent talk. Any questions from the audience? Fan Feng, please go ahead.
Hello, Hao. Very interesting
Hello.
work. Can I ask you about on some you you said your simulation seems to include like 4 kinds of energy terms, I suppose. So there is a Frank energy term. So I was always wondering, so which energy term play more significant roles? For example, so in my understanding, for example, Frank energy would contribute very little to this.
That's true.
Soft elasticity behavior, right?
Yes.
That's true based on your simulation. So basically, have you checked with, for example, the percentage of the contribution from those different energy terms?
Yes, yes, that's a good question. So actually, the Frank elasticity, as you would notice that it is of like 3 orders of magnitude smaller compared with like the elasticity of the liquid crystal elastomer and also the viscosity. So basically, the main contributor would be the elasticity itself and also the viscosity. They are of the comparable scale, and Frank elasticity would be more likely like serving as a regularization of the fine microstructures, such as you see that there is a stripe or like the interface, basically defining the interface thickness and also help us stabilize our numerical simulations.
Okay, I see. So can you go back to your page 15, probably?
Yeah.
Okay, so if I understand correctly, so the experiment starts with like a polydomain.
Yes.
Liquid.
Yes.
Pneumatic phase, polydomain pneumatic phase.
Yes.
Then you stretch it with this in-plane string, equibaxial or not equibaxial.
Yes.
So what you observed is that so the director gonna orientate.
Yes.
Within the plane. I mean, from the 3rd dimension, for example, it will orientate along within the plane, I think.
Yeah, that's a good question. So maybe let me ask it in.
I mean, after stretching, the directors will just align within the plane, I guess. I don't know.
Yeah, let me answer this question. So, so the color I'm showing you here is only the in-plane, is the angle of all the liquid crystal molecules with respect to the x-axis. Okay, so the color is only showing you the in-plane orientation, and this wide angle X-ray scattering is also showing you the in-plane reorientation, orientation of the liquid crystal molecules. But we also have a study which is telling us the out-of-plane reorientation. So here is some results. I think you are.
Yes, exactly.
Yeah. So here we have some statistics about the 3-dimensional, the 3D statistics of the orientation, where the S tensor is defining as this, and the SM is basically a number that is indicating how many of the molecules are orienting in the X direction, and X is the difference of the other 2 directions, that is the Y and the Z direction. Z basically is the out of plane direction. So if the value is larger, then basically means that, let's say the SM is larger, it means that more molecules are orienting in the X direction.
Yeah.
And X is a difference, because it is a difference, if we look at the figure, we would see that it first increases and then decreases. What it means is that it first does the it first does the reorientation in the out of plane mode, so that basically all the molecules are lying down into the plane, so that the z direction eigenvalue is decreasing very fast, so that the x is increasing, so the difference between y and z is increasing. And then finally, at the end, you would see a decrease. Basically, y and z directions are becoming the same because they are all orienting into the x direction, so that the y and z are diminishing together.
Okay.
So
Okay,
that's
I see. So you mean it will just orientate to the plane first, then
yes,
somehow distribute this x y
yes.
orientation.
Yes, so basically they do the, so all the molecules are lying down into the plane first, and then do the reorientation in plane.
Okay, that's quite interesting. Yeah, thanks.
Yeah.
Okay, that's all my question. Thank you very much. Very interesting talk.
Hi, Jin, please go ahead.
I have a general question. So is there some like these materials in nature or for biotissues, just like behave like a liquid crystal elastomer, have those microstructures?
Actually, I'm not sure if there is any biotissues, but I know that there are a lot of like human-made materials that having the similar behavior. Like say there are like fiber reinforced composite that they have the small fibers that is serving very similarly to the liquid crystal molecules, so that they have a similar behavior and a similar energy, but because they are usually the previous studies are using like hard matrix, they're not like these soft polymers, so they have a little bit different structure, but it is of the same spirit. And of course, you would know that the shape memory alloy, like the material, the metals, they would have a very similar behavior like this, because the liquid crystal lattice is orienting differently, just like this liquid crystal molecules.
Got it. Thank you, Hao.
Hi, colleague, please go ahead.
Yeah, thanks for the really nice talk, Hao. I had a similar question to what Jin had, and I don't even know if you can maybe even answer this question, but I was just kind of like trying to think about this in terms of like things like collagen, for example, which also forms kind of like fibrillous structures, and they're also like proteins in general that have like a crystalline domain, and then they have like a more kind of a more loose or like squiggly domain. And I was just trying to think about how those properties, those kind of materials, like those proteins or those kind of like collagen fibers, if they can behave similarly or very differently to the liquid crystalline elastomers that you described. It's just a general question. I'm just curious.
Yeah, first I have to say sorry because I don't know much about the bio tissues, but I'm sure that if there is I think for materials that has some anisotropy, like say if you have maybe have rod-like bacteria or like cells, then because of their mobility and the rearrangement, you might have a similar microscopic behavior that you might be resulting from that anisotropy. And I think that's certainly an interesting a field that might not be studied before. Yeah. Like say for the artificial muscles, actually liquid crystal elastomer is been serving as a potential candidate for like artificial muscles, because they have a very similar structure. Like muscle has like this all aligned fibers, like muscle fibers, and liquid crystal molecules also have this alignment. So in terms of that, there are some similarity, but they have not explored that the rearrangement or the orientation or this behavior. But there are certainly some studies that is going on there.